In the previous sections, we've talked about two types of pneumatic fan clutches, air-engaged and spring-engaged. Let's take a moment to take a look at the benefits of each type. In this system, air pressure is only applied to the fan clutch during engagement. In a normal application, the fan clutch should be in the on position less than 10% of the time, which means the air pressure is only applied to the fan clutch 10% of the time or less, and the air seals are only working 10% of the time or less. Since air seals are a primary cause of failure, a benefit of the air-engaged fan clutch design is longer-lasting seals, which may result in longer life in the fan clutch. This fan clutch requires air pressure to engage. If there is fault in the air system, the fan clutch will fail in the disengaged position. In this system, it is the lack of air pressure that engages the fan clutch. Normally, the lack of air pressure comes from the thermo switch sensing a rise in engine coolant temperature, but any lack of air pressure engages the fan clutch. From a pneumatic standpoint, this method is considered fail-safe, because if there is lack of air pressure due to a fault in your air supply, the fan clutch will fail in the engaged position. Prior to 2001, Horton Industries manufactured fan clutches using the air-engaged method, and Borg-Warner and Bendix manufactured fan clutches using the spring-engaged method. By the late 1990s, the industry generally indicated that it preferred the spring-engaged method of engagement. In 2002, Horton engineered and launched a spring-engaged design called DriveMaster. The GoldTop rebuild kit from Kitmasters is our solution for this product. Moving forward in this video, we will discuss the common causes of failure in spring-engaged fan clutches, and we'll show you how Kitmasters has solved these problems. The primary cause of failure in a DriveMaster fan clutch is pulley bearing failure. These pulley bearings have historically failed at a higher than acceptable rate. There have been many attempts to improve the quality of these pulley bearings. The competition has changed bearing manufacturers, changed bearing grease, changed bearing seals, improved the match and ground process, increased the number of rolling elements, changed the bearing design to a double row angular contact or DRAC, changed the bearing design to a longer DRAC. While these various modifications to the pulley bearings have improved the quality of the fan clutch and reduced premature failures, at Kitmasters, we believe that the bearings themselves are not the real problem. Kitmasters believes that the real source of premature failure in the spring-engaged fan clutch design is torque. Torque in a fan clutch is defined as the fan clutch's ability to engage the fan blade and sustain the engagement until the engine temperature returns to normal levels. Every fan blade requires a certain amount of torque, and every fan clutch produces a certain amount of torque. The factors that affect how much torque a fan clutch can produce include the strength of the internal spring or springs, and the shape and quality of the friction material. The interplay between the spring pressure and the friction material is what drives fan clutch torque. The first OEM fan clutch design advertised 2,100 inch-pounds of torque. At the time that this fan clutch was designed, the biggest fan blade in our industry was a 9-blade 28-inch fan. This fan blade, spinning at maximum normal RPM, required less than 2,100 inch-pounds of torque, so the fan clutch was adequately designed for the application. Unfortunately, diesel emissions requirements happened around the same time. As the emissions requirements came into effect, the engines began to run hotter. The hotter running engines required more aggressive cooling packages. More aggressive cooling packages meant bigger fan blades. The industry moved from a 9-blade 28-inch fan to a 9-blade 30, to a 9-blade 32, to an 11-blade 30, to an 11-blade 32, to an 11-blade 34, and to an 11-blade 36-inch fan. As fan blades increase in diameter, pitch, the number of blades, RPM, and so on, the torque required by these fan blades also increases. Basically, the bigger the fan blade and the faster it spins, the more torque it requires. An 11-blade 32-inch fan spinning at 2,000 RPMs, requires about 2,400 inch-pounds of torque. An 11-blade 34-inch fan requires about 2,600 inch-pounds of torque, and an 11-blade 36-inch fan requires about 2,800 inch-pounds of torque. In these examples, you can see that certain fan blades exceed the highest possible torque produced by the OEM fan clutch. What happens when a fan clutch engages is it slips a little bit and then it holds. But as the RPMs increase, the fan blade has a thrust factor, just like an airplane propeller. It wants to pull away from the fan clutch. So, as the RPMs increase and the thrust factor increases, the fan blade begins to pull the fan plate away from the friction material, decreasing the amount of torque that the fan clutch is producing. When this happens, the fan clutch begins to slip. What happens when a fan clutch slips? It causes massive internal heat. What does massive internal heat cause? Bearing failure. Lack of torque is the problem. To compensate for this, the OEM has modified the design to increase the spring pressure slightly, which increases the torque to 2,400 inch-pounds. Along with the various bearing improvements, this has helped to reduce premature failures. Kitmasters also believes that increasing the torque produced by the fan clutch is a key ingredient to solving the problem of premature failure. The following demonstration will illustrate the torque produced by the OEM fan clutch and the GoldTop fan clutch. What we have here is the current OEM design. It's engaged with all of its spring pressure and all of the holding power of its friction material. What we'll do is simulate the fan blade at high RPM and force the fan clutch to slip, and this meter will read out, in inch-pounds, how much torque the fan clutch produced. As you can see, the OEM clutch produced just over 2,400 inch-pounds of torque. When you install the GoldTop rebuild kit, here's what happens. £5,258. When you install the GoldTop rebuild kit, you upgrade from 2,400 inch-pounds of torque to over 5,000 inch-pounds of torque. Now, even when you apply the effective fan thrust, you have a fan clutch that is more than capable of handling any fan blade that exists in our industry. The GoldTop rebuild kit from Kitmasters is your solution to premature fan clutch failures. The GoldTop comes in 4 configurations. The first and most popular configuration is part number 14-256. This part number will rebuild around 90% of the on-off DriveMaster fan clutches on the market. The second part number is 14-256-1. This part number will rebuild right around 10% of the on-off DriveMaster fan clutches. This fan clutch is identical to the 14-256 with the exception of the bearings. The 14-256 comes with 2 6209 bearings, while the 14-256-1 comes with 1 3209 bearing. The remaining 2 GoldTop configurations are very rare, but do come up occasionally. Part number 14-200 is the same as the 14-256, but comes with a 2-inch fan pilot. And likewise, part number 14-500 comes with a 5-inch fan pilot. One of the benefits to a spring-engaged fan clutch that was discussed earlier in this chapter is that the fan clutch is considered fail-safe. This refers to the fact that, unlike an air-engaged fan clutch, if you lose your air pressure, the fan clutch fails in the engaged position. In the older air-engaged fan clutch, when you lost air pressure, the fan clutch failed in the off position. Because of this, the air-engaged fan clutches were designed with a come-home feature. You could manually bolt the friction plate to the pulley, thereby manually locking up the fan clutch. The fan clutch would operate fully locked up until the driver could return to the home terminal, where the fan clutch could be repaired or replaced. When the OEM switched from air-engaged to spring-engaged, they eliminated the come-home feature. Presumably because the fan clutch already fails in the engaged position when you lose your air supply. However, the term failsafe only refers to what happens when you lose your air pressure. What happens to the fan clutch when you lose your friction material? All friction material will eventually wear to the point where it can no longer engage the fan clutch. This may happen naturally due to normal wear, or this may happen prematurely due to some fault in the fan clutch. Either way, when you lose your friction material, you fail in the off position, and there is no longer a manual come-home feature designed into the fan clutch. For this reason, the industry has asked kitmasters to reincorporate a manual lockup feature in the fan clutch. Kitmasters did the industry one better, and we invented AutoLock. AutoLock is a system designed into our GoldTop rebuild kit and GoldTop remanufactured fan clutches that will automatically engage the fan clutch when the friction material is worn near the end of its life. As the friction material wears, the fan plate moves deeper into the body of the GoldTop assembly. Eventually, it will move far enough to come into contact with the internal AutoLock seal. When this happens, the surface area of the internal air chamber is reduced to a point that the clutch will not accept enough air pressure to overcome the spring that is engaging the fan clutch. Without enough air pressure to hold the spring back, the fan clutch remains engaged. In short, when the friction material nears the end of its life, the fan clutch becomes fully engaged and stays fully engaged. The driver may return to the home shop at their own convenience to have the fan clutch replaced at their own controlled cost by their own trusted labor. No tow bills, no out-of-town shop rates, no unapproved parts installed, and most importantly, no downtime. AutoLock is the patented come-home feature designed exclusively for the GoldTop rebuild kit and GoldTop remanufactured fan clutch.